Hey guys, this might be one for the math nerds. I'm a huge fan of Numberphile. Check out their channel on YouTube if you haven't yet. And about 1 or 2 weeks ago they published this video about a numerical sequence called the Recamán sequence, where they had this gorgeous visualization of what this sequence actually is. So I was trying to figure out how did they visualize it and how would I visualize it, and here's my take on it. So the Recamán sequence, and again I highly recommend checking out Numberphile's video on it. They have an exquisite explanation of what it is and even how it sounds. The Recamán sequence is constructed in this way. Let's just put integer numbers on a line starting from 0 going to whatever you like. We start from 0. What we're going to do is we will be jumping around this line of numbers from one number to the next, depending on a value called n, which is kind of the jump width. So for the first iteration we start at 0, and for the first iteration n, our jump width is 1. Now the first thing we try is going back n number of jumps, so that would yield -1 here, which is not allowed because we're only doing this for positive numbers. So instead, let's move forward n steps, which brings us to the number 1. For the second iteration, our n equals 2, and again, the first thing we try is getting back 2 steps. Again, this would take us past 0 on this side, so instead, let's move 2 steps forward, which is 1 plus another step, and we arrive at 3. For the third iteration, we set n to 3, and again, the first thing we try is going back 3 steps from our current point, so 1, 2, 3, which would bring us to 0, which in theory would work. However, we already visited 0, so we've already been there, and that is not allowed either. So again, let's move forward n steps. In our case, let's move forward 3 steps, which brings us to 6. Fourth iteration, now it finally gets interesting. We again increase the number n to 4 and try to go back 4 steps. So 1, 2, 3, 4, which brings us to 2, which we haven't visited yet, so that's perfectly legal. So let's go back those steps, and we will end up at 2. Again, fifth iteration, we increase our number n to 5, and we're starting at 0.2. So again, first thing we try is going back 5 steps, which we can't do. It would bring us past 0. So let's move forward 5 steps, which brings us to 7. And we basically keep continuing like this. Sixth iteration, n is set to 6. Again, we try to move back 6 steps, which would bring us to 1, which has already been visited. So again, instead, let's move forward. 7 plus 6 brings us to number 13. Which already yields an interesting structure and pattern. However, to finalize this thing, what we do is we check if we did 2 consecutive jumps in the same direction. For example, here we went forward, and again we went forward. And to make this look a bit nicer, we select these arcs here, where we went forward 2 times, and just flip them on the other side. Basically, we invert their direction. So we end up with a pattern like this. So this is one part, constructing the sequence. And the first thing we have to do is construct this sequence of numbers here. 0, 1, 3, 6, 2, 7, 13, and so on and so forth. We have to construct the Recamán sequence before we can visualize it. So to generate the sequence, I'm going to drop down a geo node, dive in there, delete the file node, the usual stuff, and then I'm going to drop down an attribrangle this time. I'm going to set it to run over details, so it'll execute only once. The first thing I'll have to take care about is how many iterations do I want to run this? How many jumps on my line of numbers am I going to do? And I want to dial that in with a slider, so let's call this one numIter for num iterations. And this should be an integer. Let's call it iterations. Create the interface. Here we go. Let's set it to, I don't know, 32. For now. Next, I need a list to store the actual sequence that we're going to generate. Let's call this list sequence, and it should be an array, so square brackets. And before we start iterating and doing our jumps, we need to initialize a few conditions. And the first thing I want to initialize is the first number in our sequence, because we're starting from 0. So let's add that to our sequence list using the push function. And to sequence, we want to add the number 0. Next, let's start our iteration. We want to have a loop that runs from 1 for our very first n to the number of iterations that we set up down here. So let's initialize our variable n to 1. We want to run this as long as n is smaller or equal to the number of iterations. And within each iteration, we want to increase n by 1. And of course this here is spelled sequence, not a squince. There we go. So the next thing we have to do is to translate all these conditions that we went over into code. And here's a hint, kind of a shortcut. It's a bit cheating admittedly, but why not? So on the internet there is this very useful thing, the online encyclopedia of integer sequences, which is probably the nerdiest thing that I've seen this week. and they archive number sequences and how they are constructed. And while the way they describe how these sequences are constructed might be a bit hard to understand, it is really useful when you're implementing these sequences. So Recamán sequence goes like this here. So A is the number that we're going to put into our list, and the first number, that means the number for n equals 0, is 0. We already put that into our array, and now we're iterating. For n bigger than 0, our current A number, an, equals to the previous number minus n if this expression here is positive and if we didn't visit it yet, so if it's not in the sequence yet. And if this is not the case, the number we're generating in this iteration, A, is equal to the previous value of A plus n. Admittedly, it might take some time to wrap your head around this. However, for programming, for coding, this is a really helpful description. So let's put it on the one side of our display next to our Houdini code here. So let's first generate the first case here. So let's create an integer, call it A, and it should be equal to our previous A. So that is stored in our sequence. And the previous one is just n minus 1 minus n. But this should only be our next A if it is positive and not already in the sequence. So let's check that if A is bigger than 0, so it's positive, and if it's not in the sequence. So we'll have to find if the current value of A that we just calculated has already been stored into our sequence list here. And we can use one function that's called find, which will return if a given integer value is stored within an array or not. And find, when we open up the help page for that, you can see it takes two arguments, the name of the array in which we're going to search for the value and the value itself, and it will return -1 if no matching value has been found. So if the value is not in the array yet, it'll return -1. So let's try finding within sequence our current value, and if this is -1, so if this is smaller than 0, it's not in there, so we don't have to do anything else because we can just use this value for A that we calculated up here. However, if this is not the case, so else, let's go back to our encyclopedia page. So if this is not the case, then we're going to calculate A using this formula. So A equals the previous value of A that's been stored in sequence plus n, like this. And now after we calculated our value for A, let's append it to the sequence, just pushing it at the end, like this. And finally, let's write out our sequence as a detail attribute, just using a shorthand integer array. Let's call it sequence equals to sequence, like this. Keep our fingers crossed, maybe save this, and let's go full screen on Houdini again. Head over to the geo spreadsheet and to the details here, and you can see these are the values of the Recamán sequence. So now that we constructed the Recamán sequence, let's draw those arcs here. Take, for example, this arc here, and this is the arc leading from the number 2 to the number 7. So how would we go about drawing these arcs? For drawing this semicircle, we need two things. We need the radius and the center point. So let's find the center point, and the point from which we jumped to point number 7 is number 2. So what we did is this jump here. Let's calculate the distance between those two here by taking 7 and subtracting 2 from it, so the distance here is 5. That's the diameter of our semicircle. To find the center point and the radius at the same time, let's just take the half of our diameter, which will yield the radius, 2.5, because what we did is we divided 5 by 2, which can also be written out as a multiplication. So 5 is the diameter multiplied by 0.5 equals the radius of 2.5 here. And to get the final coordinate of the arc center, let's subtract this, the radius, from our target point's position. So from 7 we subtract 2.5, which brings us at the center of this semicircle, the coordinate 4.5. And all that's left to do, now that we have the radius and the center of our semicircle, is just iteratively generate points that form this semicircle by using our old and trusty sine and cosine functions. In Houdini, to create those semicircles, again, I'm going to use an attribrangle, which I'll set to run over details only once again. And there's only one thing I want to be able to adjust with the UI, which is the subdivision of our circle. That means how many in-between points our semicircular curve will have. So let's create an integer for that, call it subdiv, maybe subdivs, and let's create a slider for that. And create the user interface here. Let's set it to maybe 64 points per semicircle. Next, we need to load in that detail attribute storing the Recamán sequence. Let's call it again sequence equals to integer array that we called sequence like this. And of course, this has to be an array too, like this. Now, before we start iterating over those individual entries in that list of numbers, we need a few variables set up. The first storing what our previous point has been. So the way we'll be working on this, we will always be looking from the point where we arrive to the last point we've been. So let's first initialize our previous number. By default, this should be set to 0. First number is 0. Also, for when we decide if we want to flip a semicircle, for the case that we went 2 steps in the same direction, I need to store the distance of the previous jump that we did, and I'm going to store that in an integer called previous dist that we initialize to be 0 as well. And finally, I want to store the direction in which the arc is going, so if it's going above my number line or below my number line, let's call it dir for direction. And if it's 1, let's move it in the one direction, and if it's -1, let's move it in the other direction. So now we can finally start iterating over those values in our list here. So let's use a for each for that. We're always reading out the number a out of our integer list called sequence. So each iteration we're taking one value out of sequence, starting here, and writing it into a, and then doing something with it. First we want to check if a is actually bigger than 0. And if it is, we're going to do something. And if it is not, we're going to do nothing for now and just store our value of a that we just read in this case is 0, in our previous number variable. So that no matter how often we run the for each, after each loop, the current value of a is stored in the previous number. Now, if a is bigger than 0, let's first check the distance. Let's calculate the distance. So float dist for distance equals to a, our current number, minus the previous number. Next, let's check if this is the second step into the same direction that we're taking. So we check if our current distance is positive and if our previous distance has been positive as well. So this means that we've taken a step into the positive direction in the previous iteration and also now taken a step into the positive direction. So if that's the case, we're just gonna invert the direction. And also for the other case that we've taken 2 steps in the negative direction, let's do the same thing. So if dist is smaller than 0, if it's negative, and our previous distance has also been negative, then let's invert the direction. Like so. Next, let's calculate the center of our semicircle. And the center can be either our current a minus our distance divided by 2, or the previous position that we came from plus the distance divided by 2. Let's calculate it the way we did it on our diagram. So let's take our current position minus the distance times 0.5, that means divided by 2. And the center should be 0 on the y and 0 on the z-axis. Or let's maybe turn this around and make this a bit more elegant. Let's first calculate the radius. And it is the distance times 0.5. And then we can just use that down here and go a minus radius. Like so. Now what we can do is use that center and the radius to actually generate all those intermediate points that form up the semicircle. And I'll use an array, and I'll call it PTS for points, to store in those points that we will create now. What I first want to calculate is the angle per step that I have to take to form up a circle. So how many degrees in radians will I go each step of my semicircle? Let's call this float angle increment. As we are working in radians, not in degrees, my semicircle goes from 0 to pi. So in order to arrive at my individual increment, I'll just have to divide pi by my subdivision steps. So pi is a constant. If you're working in 16.5, just drop down pi divided by float of the subdivs. And I will convert subdivs into a float value here explicitly, just to be sure that I'm not getting any mistakes by Houdini assuming that pi should be an integer and then only dividing 3 by some integer number here. Also take note that if you're working on an older version of Houdini, first you should update, there is no reason not to. And second, if for some reason you can't update, you'll have to specify pi beforehand. So just dropping down something like this, float pi equals to 3.1415926. I think that's precise enough for our case. However, as we are working on 16.5, let's just delete that. Pi is now a constant, we don't have to specify it by ourselves. Now that I have the angle that I want to increment by each iteration, let's drop down a loop to actually generate those point coordinates. So I want to iterate over a float value, and let's call it angle. And it should start at 0, because again, we want to draw an arc from 0 to pi. So as long as the angle is smaller or equal to pi, let's increment it by the angle increment. So angle plus equals angle increment like this. And I think, yeah, I did a typo there. So it's angle increment, not angel increment, like this. Let's first calculate the x and y offset for our point on our arc. So the x is calculated by our trusty old cosine. I'm just going to take the cosine of the angle and multiply it by the radius we've already calculated. For the y, let's use the sine function. Again, multiplied by the radius. And in here, I want to take into account the direction. So I'll multiply it with the direction, which will be negative to draw a semicircle below our line of numbers and positive to draw a semicircle above our line of numbers. Let's create a vector, call it offset, using our x and y coordinate that we just calculated, and z should be set to 0, like this. Using that offset, let's calculate the actual position of our point by using our center that we just calculated and adding to it the offset, like this. Now finally we can use this position we calculated to actually create the new point. Let's call it new PT, and use the add point function on our 0 geostream to create a point at the position we just calculated. And finally add this newly created point to our points list. So we're just going to push 2 points, our newly created point, like this. So that's the for loop where we calculated the individual positions on that semicircle. Now let's finally draw this semicircle using a function called addPrim. To a 0 geostream we want to add a polyline. That's just a line, and we want to add all the points that we stored in our points list, PTS, to that polyline. And finally, before we can call this one done, what I want to do is, up here I used my prevdist variable to check if we did 2 steps in the same direction, so I'll have to update my previous distance down here to be able to meaningfully use it in the next iteration. So I'm just going to go previous distance equals to the distance we just calculated and used and don't need any more in this iteration. Okay, fingers crossed. Oh yeah, we're getting a squiggly line here because we set our distance here to be a float number, and up here we set it to be an integer. So let's make that a float as well. No squiggly line anymore. Let's have a look at the scene view, and we can see now we are getting those lines here. Very nice. Let's try to increase the number of points we're calculating here in our first wrangle. Zoom out a bit. Yep, that is working. So some remarks about what we just did here. First, to understand an algorithm, it is really helpful to have 2 things. On the one hand, an overall understanding of what the algorithm actually does. And this can best be described in human-readable text or words, as the Numberphile guys did, for example, with this one. I think I wouldn't have gotten what the Recamán sequence is so quickly had I not watched the Numberphile video. On the other hand, for implementation purpose, it is really helpful to have a description like this here in the encyclopedia, which is written from a logical mathematical standpoint, which is what we will be finally dealing with when writing code. So again, I think both explanations are equally valuable, maybe the Numberphile explanation even a bit more so, because it allows people to quickly understand an algorithm. However, if you want to implement it, you will need a mathematical description of it. So really helpful, both versions. Then here where I calculate the Recamán sequence. This might not be the quickest way to calculate this thing. It's just the most compact, most straightforward form. For example, what we're doing here is each iteration we're using a search function to search our array for a value that we are trying to match. And this is usually not that quick. However, in our case, as we are dealing with very few iterations, we are still getting away with it and getting okay performance. However, if you were to implement something that needs to be a bit more performant, you would look for other algorithms to calculate this thing. Then, as for creating the geometry, the major part here is just calculating those in-between points. I mean, it takes up this amount of code here. This is just for generating those semicircles here. So you could, for example, write a much more compact or a bit more compact version of this if you went for triangles to connect those jumps, for example, just like going straight lines, 2 straight lines per jump. And finally, you can use any type of connection that you like to connect those jumps and visualize them. So I'm kind of hoping and looking forward that you guys create your own versions of visualizing those jumps using different kinds of geometry and geometric algorithms. So that's been it for this week. I want to say a very special thank you to our supporters on Patreon, especially Mohammed Al-Abri, Mikhail Ivanov, Robert Bryan Jr., Refik Anadol, Chris Hebert, Nick, John Coons, and Joseph Howerton. Thank you guys. So see you soon, and it's cheers and goodbye.